Good day everyone. This is RHC. Today we will discuss about the steel beam design. Before we continue, please don't forget to subscribe to my channel, like this video and click the notification bell so that you will be notified once there's a new uploaded video. Also, please join our YouTube community to avail the exclusive perks depending on the level. And without further ado, let's start our discussion. A beam primarily supports transverse loads, loads that are applied at right angles to the longitudinal axis of the member. Beams, then, are primarily subjected to flexure, or bending. It's easy to design a beam that is loaded about a single strong or weak axis and through the member's shear center, eliminating torsion. When the loading conditions vary from these, however, beam design becomes more complex. The following are the limit states that should be checked when designing beams. Yielding. Lateral torsional buckling. Flange local buckling. Web local buckling. Tension flange yielding. Local leg buckling. Local buckling. Shear. Local buckling can be prevented by using established limits on slenderness ratios for various elements, such as the flanges and webs of the members. Depending on its slenderness ratio, each element is classified, from the lowest ratio to the highest, as compact, C, non-compact, and C, or slender, S. If the flanges and webs are compact, the limit state for the entire member will be reached before local buckling occurs. Flexural stresses are frequently the controlling design criteria for beams. The flexural resistance capacity of a beam is a function of all the following: steel yield point, axis of bending, compact or non-compact section, and the distance between lateral bracing points of the compression flange of the beam, LB. The type and extent of the bracing of a beam's compression flange determines its potential failure modes: yielding, inelastic torsional buckling, or elastic torsional buckling, and consequently the appropriate formulas to use for designing or analyzing beams. These three modes are commonly referred to as flexural zones 1, 2, and 3. In flexural zone 1, illustrative example, yielding, the compression flange of the beam is braced laterally at distances less than or equal to LP, the limiting length for plastic bending. The lateral unbraced length, LB bracing, prevents the compression flange from buckling, thereby enabling the maximum stress to reach the yield stress and develop the full plastic moment of the section. In flexural zone 2, illustrative example, inelastic torsional buckling, the compression flange is braced laterally at distances greater than LP but less than or equal to LR, the limiting length for inelastic torsional buckling. With bracing spaced at this distance, inelastic torsional buckling occurs before the yield stress is reached. MR is the moment strength available when LB equals LR for service loads where the extreme fiber reaches the yield stress, phi, including the residual stress. In flexural zone 3, illustrative example, elastic torsional buckling, the compression flange is braced at distances greater than LR. This results in elastic torsional buckling. Regardless of the flexural zone, the basic design formulas for designing flexural members for strength are based on design requirements given in AISC specification Chapter B. Example: Zone 1 bending. The 30 feet beam shown is laterally supported for its entire length. The beam supports a uniform dead load including the beam weight of 0.30 kip per foot and a uniform live load of 0.70 kip per foot. Material properties. ASTM A992 steel. Fy equals 50 ksi. Fu equals 65 ksi. Select the most economical beam that complies with the deflection criteria for floor beams in the IBC. Solution. Calculate the required flexural strength. The loading is: for Lrfd, the ultimate factored load is 1.2 times dead load, plus 1.6 times the live load, and this is equals to 1.48 kips per foot. For ASD, the allowable load is 1 times dead load, plus 1 times live load, and this is equals to 1.0 kips per foot. Computing the moment. For Lrfd, the ultimate moment is equals to ultimate factored load, times L square over 8, and this is equals to 166.50 feet kips. For ASD, the allowable moment is equals to allowable load, times L square over 8, and this is equals to 112.50 feet kips. Calculate the moment of inertia required to comply with the IBC, remembering that deflections are calculated on service loads and not factored loads. The allowable deflection and required moment of inertia for the live load are: the deflection is equals to clear span length of beam over 360, and this is equals to 1.0 inch. And for the moment of inertia, this is equals to 5 times the allowable load times to the L to the fourth, over the product of 384 times the modulus of elasticity E and the service load deflection. For the total load, the deflection is equals to clear span length of beam over 240, and this is equals to 1.5 inches. And for the moment of inertia, this is equals to 5 times the allowable load times to the L to the fourth, over the product of 384 times the modulus of elasticity E and total load deflection. Therefore, I required is governed by the live load deflection, and the minimum moment of inertia is 440 inch to the fourth. Because the beam is laterally supported for its full length, the unbraced length of the beam is 0 feet and the full plastic moment, MP, will be obtained. Therefore, CB is 1.0, and the beam is in the plastic range, zone 1 bending. Next, is we need to calculate the required plastic section modulus. For Lrfd, the required plastic section modulus is equals to ultimate moment of the beam over the phi sub b times the value of Fy. And with condition that the ultimate moment must be less than or equals to the product of phi sub b times the normal moment. Also it must be less than or equals OT the product of phi sub b time the value of Fy times plastic section modulus. Thus, the required section modulus is equals to 44.40 cubic inches. For ASD, the required plastic section modulus is equals to allowable moment times omega sub b over the value of Fy. And with condition that the allowable moment must be less than or equals to the value of normal moment omega sub b. Also it must be less than or equals OT the product of the value of Fy times plastic section modulus over the omega sub b. Thus, the required section modulus is equals to 45.09 cubic inches. Basing the selection on strength, for AW 14 times 30, CAISC Manual Table 3-2. For Lrfd, the moment of inertia is less than the computed value, thus the section is not OK. For ASD, the moment of inertia is less than the computed value, thus the section is not OK. Basing the selection on IREC for deflection, for AW 18 times 35, CAISC Manual Table 3-2. For Lrfd, all the value of plastic section modulus, Zx, the product of phi sub b times m sub px and the I sub x are all greater than compared to the computed values, thus the section is OK. For ASD, all the value of plastic section modulus, Zx, the product of phi sub b times m sub px and the I sub x are all greater than compared to the computed values, thus the section is OK. Thus, the design of the member is controlled by deflection rather than by yielding, and use AW 18 times 35 section. That's all for today, thank you and God bless.